Hello lovelies, in this video we're going to be going through your AQA A-Level Chemistry Paper 3, the predicted paper that we've written for 2024. Now, the really important thing for you to look at when we're going through this is your exam skills as well as your knowledge. What do you need to be able to do? What skills do you need? What do you need to practice in order to get those high grades?
Energy changes take place when water dissolves compounds and when water changes its physical states. For example, when ammonium chloride dissolves in water, a temperature decrease is measured. Now, that's an important fact because that tells us that when ammonium chloride dissolves in water, we have an endothermic reaction taking place. Here we're asked to define in words the term enthalpy change of solution. And this is one of those definitions that you just need to have memorised. Okay, so the enthalpy change of solution is the enthalpy change for 1 mole of an ionic compound to dissolve in sufficient water to form an infinitely dilute solution. So I think that definition is quite a mouthful. So if you're not 100% familiar with this definition, then I would recommend you pause the video in a moment and get this definition copied down so that you can get learning it. Okay, so enthalpy change of solution is the enthalpy change for 1 mole of an ionic compound dissolving in sufficient water to form an infinitely dilute solution. Okay, so next up, we're told that ammonium chloride can dissociate to form ammonia and hydrochloric acid. The enthalpy change for the decomposition of NH4Cl is difficult to determine directly by experiment. State the reason for the above statement. So, of course, this is an endothermic reaction. So for it to go in that forward reaction here, we're going to have to encourage it to shift in this endothermic direction. And the way that we would do that is by increasing the temperature. This means that we need to supply heat to the system for this reaction, this decomposition to take place. And that is the reason why the enthalpy change for the decomposition of ammonium chloride is difficult to determine directly by experiment. Now we need to calculate delta G for the decomposition of ammonium chloride at 1000 degrees Kelvin. We're told that at 25 degrees C, Gibbs free energy, delta G, is equal to positive 91.2 kilojoules per mole. So let's start off by writing down the equation that we need here. So we know that delta G equals delta H minus T delta S. Now in this question, we're told that when delta G equals 91.2, the temperature is equal to 25 degrees C. Now that's great. However, for this equation, we need to use Kelvin. So let's add 273 to 25 and we get 298 Kelvin. So now that we know this, and we also know as well that delta G at this temperature is 91.2, and we know from the previous page that delta H is equal to 176 kilojoules per mole, we've got everything we need to work out what that entropy change is. And that entropy change will be the same regardless of the temperature. So what we're going to do now is we're going to substitute these numbers in. So therefore, we're going to get 91.2 is equal to 176 minus 298 times by delta S. Now rearranging this to find delta S, first things first, let's subtract the 176 from both sides. That gives me minus 84.8 equals minus 298 delta S. And now if we divide through by the minus 298 and cancel out the negatives, we end up finding that delta S is equal to 0.2846, and that's going to be in kilojoules per Kelvin per mole. So now that we know delta S here, we can work out what delta G is at this new temperature, because delta H and delta S will remain the same regardless of the temperature. So we now know delta S is 0.2846 because we just calculated that. We know that the temperature is 100 Kelvin now. And delta H is still the same, it's still positive 176. So we can put these numbers into our equation now for delta G, and we're going to find that delta G equals 176 minus 1000 times by 0.2846. So if we end up popping that into the calculator, then I end up finding that delta G is equal to minus 108.6 kilojoules per mole. And so there we have it, that is what delta G is. So now we're asked to state and explain whether this reaction takes place spontaneously at 1000 degrees Kelvin. So in order to answer this, we need to know one simple fact. We need to know that reactions take place spontaneously when delta G is negative, or less than 0, we could say. And so in this case, as we can see that at 1000 degrees Kelvin, delta G is equal to minus 108.6, which is negative, we can indeed say that yes, the reaction does take place spontaneously. And our explanation is simply stating that delta G is negative, or less than 0. A student wants to find the enthalpy change of solution when solid ammonium chloride dissolves in 50 centimetre cubed of water. Here we're asked to suggest an experimental method to find the enthalpy change of solution of ammonium chloride. Okay, so this is a really important experiment, so I'm going to tell you our 4 steps here to get our 4 marks. Okay, so here we need to measure 50 centimetres cubed of water first. We're going to use a burette to measure this, and we're going to put it into a small beaker. The reason why we're not using a measuring cylinder here is because it's going to be less accurate. Okay, so now we've done that, we now need to measure the initial temperature of the water, and we're going to use a thermometer to do that. So see here, each step of the way we're saying what measurement we're taking and what apparatus we're using to make the most suitable measurement. Okay, so we've got our 2 steps there now. Next up, the next thing we need to do is add the ammonium chloride into the water, and we're going to stir it continuously. And the reason why we're stirring it continuously is going to be evenly distribute any temperature changes that occur in the water. So the final thing that we need to do is we want to record the minimum temperature of the resulting solution. And it's important that we say minimum here, okay? Because of course we have an endothermic reaction taking place, and so the temperature of the water is going to be decreased. So we want to record the minimum temperature of the resulting solution, again using that thermometer. Okay, so next we're asked to calculate the energy transferred in kilojoules when 15 grams of ammonium chloride is dissolved in the water. Here we're asked to consider that the change in temperature is 12 degrees C, specific heat capacity of solution is 4.18, and the density of solution is 1 gram per centimetre cubed. So here the equation for energy transfer is Q equals mc delta T. So when it comes to working out the mass here, the mass of this solution, we need to remember that we have 50 centimetres cubed of water. And although we add 15 grams of this ammonium chloride, it's not going to increase the volume, it's just going to dissolve in that solution. And so what really matters here is that the volume is 50 centimetres cubed and the density is 1 gram per centimetre cubed. It's using that fact that we can say that the mass is going to be 50 grams. So that's the first bit of information that we know that we have. We know mass is 50 grams, C is going to be 4.18, and we're told that the change in temperature is 12 degrees C. Remember, when it's change in temperature, that's the same regardless if it's degrees C or Kelvin, so we don't need to convert anything there. So therefore, our heat energy will be equal to 50 times 4.18 times by 12. Now that gives me 2,508 joules. And I know that's joules because if I look at the unit of specific heat capacity, it's joules per kilogram per Kelvin. However, this question wants the energy in kilojoules. So we need to divide that number by 1,000, and we end up getting 2.508 kilojoules. and that there is our energy transferred. So now we need to calculate the enthalpy change of solution when 1 mole of ammonium chloride dissolves in water. Here we're asked to include a sign and the units in our answer. So in order to answer this, we need to remember that enthalpy change is the heat energy divided by the number of moles. And we just worked out that heat energy. We found it to be 2.508 kilojoules. However, now we need to know the number of moles. Well, we know that the mass of ammonium chloride is equal to 15 grams. We were told that on the previous page. And we can work out the MR. So it's going to be 14 for the nitrogen, plus 4 times 1 for the hydrogens, plus 35.5. And that gives us an MR for ammonium chloride of 53.5. Now we know that, we can work out the moles we have of ammonium chloride. That's going to be 15 over 53.5, and that ends up giving me 0.2807. So that's how many moles I have of ammonium chloride. Now all I need to do to work out my enthalpy change is just to take my Q, my 2.508 kilojoules, and divide it by 0.28037. So popping that into the calculator there, I end up finding that our enthalpy change of solution is equal to 8.9452 kilojoules per mole. Now I've got the units there, that's great. If I look back at the question, I can see we also need to include a sign. And because we know this is an endothermic reaction, remember we were told right at the beginning of this question, in that opening line, that when ammonium chloride dissolves in water, a temperature decrease is measured, which means, of course, that we have this endothermic reaction. So we're going to finish up this question by putting a little positive sign next to our 8.9452 kilojoules per mole. And that's our answer. Make sure that you always check at the end of these questions whether it should be positive or negative. Clock reactions can be used to study reaction kinetics. Consider the following iodine clock reaction when hydrogen peroxide is mixed with a solution containing thiosulfate, potassium iodide and starch. A fixed amount of thiosulfate is present, which reacts immediately with the I2 and removes produced I2 from the reaction mixture. Once all the I2 produced has reacted with thiosulfate, any further I2 produced reacts with the starch present, providing a means to monitor the reaction rate. A student assumed that the rate of reaction is proportional to 1 over time taken for the appearance of the colour. When the reaction is carried out, the following results were obtained. So here we've got a nice table with the concentration of iodide ions, the time taken for the reaction, and 1 over time 2. Here we're asked to complete the table and plot a graph by using the data to determine the order of the reaction with respect to the I- ion. So the first thing we need to do here is to complete this table. So we need to do 1 over 300, which gives us 3.33 times 10 to the minus 3. Now notice that here the 1 over time is in 10 to the minus 3 per second, so we only need to use 3.33 here in this box. So now we need to have a look at how we plot this graph. So we need to make sure that we include the axes and the units, and we also put a scale on these axes as well. So here I've got the concentration of iodide ions in moles per decimeter cubed on my x-axis, and on my y-axis I've got 1 over time in 10 to the minus 3 per second. Now that I've done that, I need to determine what scale would be most suitable. So looking at concentration of I-, I can see it needs to go up to at least 1.1. So I'm going to go up by 0.2 each time. It's really important that we fill at least half of the space on these graphs. If we make it too small, we won't get the marks. So on the y-axis now, I can see the biggest value is 5.56 and the smallest one is 1.11. So I need to go up to at least 6 here. So I'm going to go up 1, 2, 3, 4, 5, 6, 7. I have filled at least half the space with the data that I'm going to need. So I'm happy with those scales. So now first off, let's plot 1.1 and 5.56. So that looks about there. So now we've got 0.9 at 4.42, looking good. Next up I've got 0.7 and 3.33, which will go about there. Now I've got 0.6 and 2.75, which will go just here. Then I've got 0.5 and 2.25, so that's going to go around about here. And finally I have got 0.3 and 1.11. So here we go. Those points look really good to me. And here's the line of best fit here. I can see that it's a straight line through the origin. And that's going to be really important in determining the order of the reaction with respect to the iodide ion. Hence deduce the order of the reaction with respect to the I- ion. So this is where our graph is really important. That graph clearly showed a straight line that passed through the origin. And because of that fact, we can say that this reaction is first order. And this is a 2-mark question, so we're going to give our reasoning as well. We're going to say because the graph is a straight line through the origin. Whenever we have a graph where we get this straight line through the origin, we know that the two variables are directly proportional. And of course, that's what first order means. It means that the rate is directly proportional to the concentration. Okay, so now we're asked to state the colour change observed after all of the thiosulfate ions are used up and more iodine is produced. So, for this we need to remember that starch is acting as an indicator. When there's thiosulfate present, all of the iodine ends up just reacting with the thiosulfate. However, when we run out of thiosulfate, that iodine will be remaining in the solution. And that iodine will react with the starch and turn a blue-black colour. And so that is going to be our answer here, okay? We need to remember that starch is our indicator here. It's like the opposite of biology, where actually iodine is the indicator for starch. We use a starch indicator, and when the iodine does become present, we will see this blue-black colour appear. And that's due to the reaction of the starch with the iodine. The reaction is first order with respect to hydrogen peroxide and zero order with respect to hydrogen ions. Here we're asked to write the overall rate equation for the reaction. And we should know the general form is rate equals K times by concentration to the power of their orders. Now here we know that rate equals K times by hydrogen peroxide to the power of 1 because it's first order. We said earlier that it's first order with respect to iodide as well. Remember, we worked that out in part 2. And we're also told that it's zero order with respect to hydrogen ions. So technically we could do square brackets h to the power of 0, but we should know that anything to the power of 0 is just 1. So all that we're left with here is rate equals K times by the concentration of hydrogen peroxide, in theory to the power of 1. If we included that, that's fine. And then times by the concentration of iodide to the power of 1, using what we worked out from part 2. So next up, we're asked to deduce the units of that rate constant. And in order to do this, let's rearrange the equation to get K as the subject. So here we have K equals rate over the concentration of hydrogen peroxide times by the concentration of iodide ions. So what we should do here now is instead of substituting in numbers, we just substitute in the units. So we should know that the unit of rate is moles per decimeter cubed per second, and the units for both of those concentrations is going to be moles per decimeter cubed. So what we're left with here is moles per decimeter cubed per second over moles per decimeter cubed times by moles per decimeter cubed. So we can cancel out one of the moles from the top and the bottom, and the dm-3s from the top and the bottom. Now, we have a mole left on the bottom, that's mole to the 1. And because it's on the bottom, we're going to reverse the sign. It's going to be mole to the -1 now. Same goes for that dm-3 on the bottom. We're going to reverse the sign and call it dm cubed. Now finally, we've got this s-1 here. So we're just going to put s-1 there at the end. We don't do anything with the sign, we don't make it positive, because that's already on the top of this little fraction here. So the units of the rate constant per mole decimeter cubed per second. So finally here we're asked to state the experimental measurements the student must provide in order to determine the activation energy for the iodine clock reaction. Okay, so to get the activation energy, there's two things that we need here. One is we need to measure that time taken for the blue-black colour to appear. That's going to enable us to get the rate and therefore the rate constant. And finally, the other thing we need is the temperature. Using all of these things, we will be able to use the Arrhenius equation to link the rate constant, the temperature, to the activation energy as required here. Fuel cells are a type of electrochemical cell which is used as a source of energy. Redox systems that can be used in electrochemical cells are shown below. A hydrogen-oxygen fuel cell is an electrochemical cell which can be operated in acidic or alkaline conditions. Here we're asked to write the half equations for the changes that take place at each electrode when an alkaline hydrogen-oxygen fuel cell operates. So first we need to identify which systems we need. And because this is alkaline conditions, we need the ones with OH-. Now that means that we're going to be using systems number 1 and 3. So we need to write these in the right way, okay? We don't just want to copy them down now for the oxygen and the hydrogen electrode. We need to recognise that if we look at their electrode potentials, we need to flip the most negative one. Remember that species with the most negative electrode potentials are better reducing agents, and so they can reduce those that are less negative than it. So in this case, out of these two, I can see that system 3 is the most negative, so that's the one I'm going to flip, and that's what I'm doing here. I'm just writing it so that the reactants are now the products and vice versa. So now that I've got these, I can see that the oxygen electrode is just going to be as the equation above was. Got O2 plus 2H2O plus 4 electrons makes 4 hydroxide ions. And at the hydrogen electrode, I'm going to write it in this flipped version. So I've got H2 plus 2OH minus goes to 2H2O plus 2 electrons. So now we're asked to write the conventional representation for this particular cell. And to do this, I'm going to first remind you of a few rules that we need to adhere to when working out conventional representation. First things first, let's remind ourselves that we have platinum electrodes here. We know that because all of the state symbols of systems 1 and 3 are either liquids or aqueuses or gaseous. So we need a solid electrode. Nothing there is going to help us, so we use platinum. So in our conventional cell representation, the solid vertical lines show phase boundaries, and that's when we have this change of state. The double lines, however, represent the salt bridge. And so we're going to have a double vertical line in the middle of our conventional representation, which represents, like I said, that salt bridge. So now we need to think, what are we going to put next to that salt bridge? And we end up putting the species with the highest oxidation state of each of these half cells next to that double vertical line of the salt bridge. And the final thing to mention is that the positive electrode goes on the right-hand side. So therefore, the negative electrode will be on the left-hand side. Now, looking at these electrode potentials up here, I can see that the most positive is the oxygen half cell, so I'm going to end up putting that on the positive electrode on the right-hand side, and the hydrogen half cell will be on the left-hand side. So let's get started by putting down platinum. Make sure we always put state symbols as well when doing conventional representation. So I'm going to do platinum solid to start us off. And we're on the left-hand side of this, so we're going to do the hydrogen half cell. Here we have hydrogen, and that got oxidised to H2O. So we went from 0 to +1. We said that the species with the highest oxidation state for each half cell goes next to the salt bridge. So what I've done here is first I've put the H2 in its gaseous form. Then I put another vertical line because we're changing phase again. We're going from a gas to a liquid. And I've put water down. The reason why I put water there is because that is what the hydrogen, that H2, has been oxidized to. So now I need the salt bridge, so I've got my double vertical line there. And now I'm doing my right-hand side. I know that the most positive electrode is on the right-hand side. Here I can see that the oxygen has been reduced to OH- ions. We stated before, didn't we, that the species with the highest oxidation state is next to the salt bridge. So I put O2 gas down first, then I do a vertical line to show a change in phase going to the aqueous OH-, and then finally a final vertical line to show the change in phase from the aqueous OH- to the solid platinum electrode. And there we have the conventional representation for this cell. So next up, we're asked to state the standard cell potential for this fuel cell. So to work this out, we need to take the most positive electrode potential and take away the most negative. And I always just remember it like that. It's the most positive minus the most negative. We will always end up getting a positive answer here. So in this case, the most positive was the 0.40, and then we're subtracting the most negative. So we're doing 0.40 minus 0.83, which gives us 1.23 volts. So nice and easy there. Just make sure you remember how to calculate the standard cell potential. The pressure of the oxygen in this hydrogen-oxygen fuel cell was increased. Here we're asked to explain the effect of changing the pressure on the EMF of this cell. So first things first, I think it's important to know what the overall cell reaction is here. So if we remember our two half equations, we had O2 plus 2H2O plus 4 electrons makes 4 OH-. That was our oxygen half cell. And then we had our hydrogen half cell as well, which stated that H2 plus 2 OH- makes 2H2O plus 2 electrons. So if we balance those, we can get our overall reaction here. And we can use that to determine what's going to happen when we have this increase in pressure. So looking at this, I can see that that second equation, the hydrogen half cell, needs to be doubled because we've only have 2 electrons and we need 4. So that becomes 2H2 plus 4 OH- goes to 4 H2O plus 4 electrons. So now we can combine these two half equations to make our overall reaction. I can see I can cross out the electrons, and I can also cross out the OH-. Now, a final thing we can do as well is I can notice that I've got 2 waters on the left and 4 on the right, so I can cancel out 2 from each to simplify that down a little bit more. So now bringing that all together, we get our overall equation. And we can see here we have oxygen gaseous plus 2H2 gaseous goes to 2H2O, which is a liquid. Now, this is really a reversible reaction, okay, because it can happen in both directions. In this case, we're looking at increasing the pressure. And here I can see that my reactants are gaseous. And therefore the equilibrium here is going to shift to the right-hand side. And by shifting to that right-hand side, we're going to increase the EMF. So what we can say here is that the effect on the EMF is that it's going to increase. And the reason for this is that our overall equation is going to move to the right-hand side. So now we're asked to state one difference between a fuel cell and a conventional storage cell. So the main difference that we need to know here is that a fuel cell reacts with a fuel, such as hydrogen, with oxygen to produce a voltage, whereas our conventional storage cells don't. So if you weren't aware of that difference between the fuel cells and conventional storage cells, make sure that you get a note of that down now. Solid hydrated iron 2 sulfate has the formula FeSO4.XH2O. A student follows the following steps to determine the value of X in the hydrated salt. 4.25 grams of FeSO4.XH2O was dissolved in water to form 20 centimetre cubed solution. 2 centimetre cubed of this sample of solution was acidified and titrated with 0.025 moles per decimetre cubed KMnO4 solution. 20 centimetre cubed of KMnO4 was required to react with the Fe2 plus ions present in the sample. Here we're asked to write the balanced ionic equation for the above reaction. So here we need to think about two half equations. We know that we have Fe2 plus ions present, and so they're going to go to Fe3 plus an electron. We also have these manganate ions, and I always think these particular half equations, the dichromate and the manganate ones, are worthwhile just memorising these half equations. We can work them out 100%, however they do come up so frequently that I don't think it hurts to just memorise them. If I was to actually sort of try and balance this myself, I would use the fact that I know that the manganate ion goes to Mn2+, I would just need to know that fact. And then I would look at both sides and I would say, oh, okay, so on the left I have 4 oxygens, and so I'm going to add 4 waters onto the product side because that introduces 4 oxygens on the products. So now the oxygens are balanced, but I've introduced a load of hydrogens. I have 8 hydrogens there now on the product side that I don't on the reactant side. So I add 8H+. Now the MNs are balanced, the O's are balanced, and the hydrogens are balanced. I could finally just sort of tally up, what's the charge basically on the left-hand side and the right-hand side. Remember, at the minute we're ignoring the fact that those electrons are there. Just rid of them for now. And you can see that as we have MnO4 minus and 8H plus on the reactant side, that gives us a charge of 7 plus. Over on the product side though, we only have 2 plus. So we need to go from a 7 plus charge down to, of course, a 2 plus charge. That's where these 5 electrons come in. Now that would be a way that you can work this out. However, like I say, honestly, just learn it, just memorise it. This and the dichromate one, I think that they just come up so frequently, and really, you don't get many marks in this case for working that out. Let's just learn it off by heart and then use it when we need it, okay? So, we've got the 2 half equations now. Get back to this question. We've got the 2 half equations. We've got the Fe2 plus going to Fe3 plus electrons, and we have worked out, or we've memorised the manganate ion one. Now we need to get the balanced ionic equation for this reaction. Now I'm going to look at each of these 2 equations and I want to balance the electrons. I can see that this second equation with the manganate has 5 electrons. However, the first equation only has 1 electron. So we can easily fix this just by multiplying this first equation through by 5. So I'm multiplying all of these bits through by 5, not just one of them, all of it. Now the electrons are balanced, and so we can cancel these out now. So I'm just going to cross them through because we have 5 electrons on the reactant side and 5 on the product. So now that we've done that and we've cancelled out the electrons, I'm just going to smush these 2 together. So basically all of the bits on the reactant side I'm going to smush together, and all the bits on the product side I will also smush together, imagining sort of an imaginary line just here. So in terms of those reactants, I have 5 Fe2 plus MnO4 minus plus 8H plus. That's all of the reactants once we've cancelled out the electrons. And then having a little look at the products now, I can see I have 5 Fe3 plus Mn2 plus makes 4H2O. And there we have our overall balanced ionic equation for this reaction. And there's one last thing that I want to add to it, and that is the state symbols. So we should know that all of these ionic substances are aqueous. However, the water is liquid. So that's just the final thing to add on here to have our full 3 marks. So now in part B, we're asked to calculate the number of moles of Fe2 plus ions present in the 20 centimetre cubed sample of solution used. Now I think it's really important in these questions to basically work backwards any kind of titration question, look at the last bit of information they've given you and work back through all of the numbers. So in this case, we're told about potassium manganate. We're told we have a volume of 20 centimetre cubed and a concentration of 0.025 moles per decimetre cubed. And that's what we needed to react with all of the Fe2 plus ions present. So we can use the equation C times V over 1000 to work out the moles of potassium manganate. So if we do 0.025 times 20 over 1000, I get 0.0005 moles of potassium manganate. Now, the moles of potassium manganate is exactly the same as the moles of manganate ions. Now this is where our balanced equation comes in here. Because if we know the moles of manganate, we can work out the moles of Fe2+. I can see I have a 1:5 ratio here. So for that reason, I can say that I have 5 times as many moles of Fe2+ as I have of manganate ions. So if I do 5 times 0.0005, I get the number of moles of Fe2+ that completely reacted with that manganate. And that gives me 0.0025 moles. However, there's a little trick in this. Because that little amount of Fe2+ that reacted with the manganate was just in a 2 centimetre cubed sample of it. However, this question is talking about a 20 centimetre cubed sample. Very easy to miss that information, but it's a very common thing that will come up in these titration calculations. Like we've just taken a little scoop out of the overall sample and titrated that. So it's a really easy fix, because to find the moles in 20 centimetre cubed, we just need to we need to times the moles that were in 2 centimetre cubed by 10. And so that gives us 0.025 moles of iron in that 20 centimetre cubed sample. So really do watch out for that. Make sure you've got the right volume that the question wants. So now we're asked to calculate the relative formula mass of FeSO4.xH2O in 4.25 grams of the compound. Well, remember, in the previous part of this question, we just worked out how many moles there were of Fe2+ in this sample. So when we look at this formula of FeSO4.xH2O, we just need to realise that there's going to be the same number of moles of that whole hydrated salt as there are moles of Fe2+, because there's only one Fe2+ in that formula. That means that the moles of this hydrated salt is also 0.025. Now this question, we've been told that the mass is 4.25 grams, and so we can work out the MR, because remember we know the formula that moles equals mass over the MR, and by rearranging that we can get that the MR equals the mass over the moles. So that gives us 4.25 divided by 0.025. And popping that into the calculator, I get 170 grams per mole for that MR. Next up, we're told that the relative formula mass of anhydrous copper 2 sulfate is 151.8 grams per mole. And we're asked to calculate the value of X in FeSO4.xH2O. So we need to remember that anhydrous iron 2 sulfate is just FeSO4, because it is the salt without the water. So as we're told the relative formula mass of that, and we worked out the relative formula mass of that hydrated salt, if we subtract them from each other, we're just left with the MR, the relative formula mass, of those XH2Os. So, because that actually ends up being pretty much 18, doesn't it? We can pretty much assume that there's just one water in here. Of course, we could do the formal calculation. We could say, let's take that 18.2, or whatever number you get in a question that's similar, and divide it by the MR of water. So 18. Here I get 1.0111, which I can clearly see is approximately 1. So X in this case is equal to 1. So finally here, we're asked to describe and explain the test and observations that would be observed to identify the iron 2 ion present in the above aqueous solution using an excess amount of dilute ammonia solution. So the first little bit of information that we should know is that any solution that has Fe2+ in it is going to be green. So at the start of this, when we just have our Fe2+, or we could say it as FeH2O6 square brackets 2+, that complex ion there, we have this green solution. However, when we start to add some ammonia, what we're going to get is a green precipitate form. And that's a green precipitate of FeH2O4 OH2. Or we could just write that as FeOH2. And that is our green precipitate. Now we also get another little product here that I'm just going to write for a balanced equation, plus 2NH4+. Now in this question we didn't need that balanced equation to get one of our marks, but I wanted to include it to make sure that you just get as much information as possible. So our observation here is we're going from a green solution to a green precipitate. However, that FeH2O4 OH2 is eventually going to get oxidised in the air. And as it gets oxidised, we're going to observe a colour change. We will see it slowly change colour to an orange-brown solid. And this is because when the iron 2 hydroxide gets oxidised by the air, it becomes iron 3 hydroxide. Or we could write that as FeH2O3 OH3 or FeOH3. All of those would be perfectly acceptable versions of it. So, if you're not aware of that series of colour changes, then I really do recommend that you go away and get learning it. Make your notes on it now, don't leave it till later, and just get learning it, because then you're going to make sure you get those marks in the exam. This question is about the different organic compounds. Consider the following two alkane compounds. Here we're asked to write the IUPAC names of the compounds A and B. So the way that I like to do this is I need to think, well, what is the longest carbon chain? Here I've highlighted a longest carbon chain. I can see that consists of 1, 2, 3 carbons. Now coming from that second carbon in the middle, I have 2 methyl groups. So because the longest chain is 3, the main part of the name is propane, and because we have 2 methyl groups coming off the second carbon, we have 2,2-dimethylpropane. Make sure that you write down the 2 twice, not just once. We need to write it down for each of the methyl groups. So then we do exactly the same for B now. We look for that longest carbon chain. I can see here I've got 4 carbons, so I have butane. However, I have a methyl group on the second carbon, so the full name is 2-methylbutane. When numbering it, make sure that your groups are on the smallest number possible. So we wouldn't call this 3-methylbutane, we call it 2-methylbutane. Okay, so next up, complete the sentence. Compounds A and B are structural isomers of each other. So the reason why they're structural isomers is because they have the same molecular formula, but they have a different structure or different structural formula. Alternatively, you could have said that they're chain isomers of each other as well. That still would have got you the mark in this question. Here we're asked to consider the following reaction scheme of propene. So here I can see that there's this double bond here, and we're going to break it apart, and we're going to make an alcohol. So here we're asked to draw the skeletal formula of the compounds C and D here. So first things first here, we need to recognise that we have an alkene, and when we do react it with cold concentrated sulfuric acid and water, we end up making an alcohol. So essentially what's going to happen is we're going to break open that CC double bond, and we're going to add an H and an OH group to those 2 carbons of that double bond. Now here we're going to have a major and a minor product. Now it's important that we remember that the major product forms from our most stable carbocation. And we need to know that the tertiary carbocation is more stable than the secondary carbocation, but the secondary carbocation is more stable than the primary carbocation. So in this particular case here, the most stable carbocation is going to form on this carbon because we have these other carbon groups attached to it. So for that reason, the major product is going to be the product where the OH group is attached to that second carbon. So this is what the major product will look like. We want skeletal formula. So we've got this little pattern here, and on that second carbon, the OH will attach, because that's the most stable carbocation that forms. Whereas the minor product will have the OH attached to the other carbon of the CC double bond. So now we're asked to write the IUPAC name of the major product. So I can clearly see here that it is an alcohol, and I can see that that alcohol is on the second carbon of a 3-carbon substance. So as a result then, it's going to be propan-2-ol. And that is the name of our major product. Now we're asked to name and outline the mechanism for the reaction between propene and concentrated sulfuric acid, which gives the major product. So we know we have propene, and let's remind ourselves of what that major product was. So we said it was propan-2-ol, didn't we? And so the first thing we need to do is recognise which mechanism takes an alkene group to an alcohol group. We should know that the name of that mechanism is electrophilic addition, and it's really important that we just learn that name. So now for this mechanism, start off by drawing propene. Okay, so I'm drawing it with a central CC double bond, but however you draw it will be fine. And once I've drawn this, I'm going to draw the sulfuric acid, okay? This is very important. So we've got that H to O, and then the O goes to S, and then we have 2 SO double bonds, and then we have another OH. So I'm going to make sure that I draw dipoles on this now, okay? I can see that the hydrogen is delta positive and the oxygen is delta negative. That's important because, of course, the oxygen is more electronegative than the hydrogen. Next up now, I'm going to draw on my curly arrows. I'm going to have a curly arrow move from the electrons in that CC double bond to the delta positive hydrogen, and then from the bond between the oxygen and the hydrogen to the delta negative oxygen. So we've got all of the parts that we need for our first step there now. Let's write on our second step. So when we had the curly arrow move away from that CC double bond, that broke the double bond. However, it also formed a new bond with the hydrogen. So we've got that new hydrogen here now. We also formed a carbocation by doing that. And with our curly arrow going from the O to H bond towards the oxygen, we formed an O- ion with a lone pair. Now that lone pair is going to move to the carbocation. So we've got a new curly arrow here going from that oxygen ion to that carbocation. So this forms that final bond that we need, and we form our final product here, okay? So I'm just drawing on here my final product, which shows that oxygen now bonded to the carbon. And there we have it. This is our mechanism that we need to know for the reaction of any alkene with concentrated sulfuric acid. So I hope that that's nice and clear for you. Get learning it. So now we're asked to explain why compound C is the major product of this preparation. So remember what we said earlier, this is all about the stability of the carbocation, isn't it? So we should know that the major product forms from the most stable carbocation. And that's exactly what's happened here. In this particular case, that major product was formed via a secondary carbocation. So we need to know that a secondary carbocation is more stable than the primary carbocation, which would have been the other option, which would have formed the minor product. So let's just remind you of this because it's always handy. Here we can see that the tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation. So quite simply here, to get your 2 marks, firstly, you state that the major product formed via the most stable carbocation, and for your second mark, you state that the secondary carbocation is more stable than the primary carbocation. And that will get you your 2 marks for that question. So now we're asked to describe a test tube reaction to distinguish the compounds C and D. Well, we should remember that C is a secondary alcohol and D is a primary alcohol. And we haven't actually learned any straight up tests to immediately say, oh yes, this is a primary, this is a secondary. However, we can do a series of tests. We can add acidified potassium dichromate followed by Tollien's reagent. Now the reason why this is important is because we can't distinguish between just a primary and a secondary in a single test. However, if we oxidize these using the acidified potassium dichromate, we will get two different products. C, which is a secondary alcohol, would become a ketone, and D, which is a primary alcohol, would become an aldehyde. Now, by doing this test, both of these we would observe initially a colour change to show the oxidation, which will go from orange to green. And that's all that we would see with C, because ketones do not react with Tollien's reagent. However, with D, we may well still get that same oxidation colour, going from orange to green for the dichromate. However, due to the fact that we have this Tollien's reagent, means that we're going to form a silver mirror. And that is the really critical part here that's going to enable us to distinguish between the two of them. So C, we will not see a silver mirror, and D, we will see a silver mirror form. The reaction between lead nitrate and sulfuric acid is given below. Here we've got lead nitrate plus sulfuric acid makes lead sulfate and nitric acid. Identify which type of reaction this is. So neutralization. Well, when we have neutralization, we normally have an acid plus some sort of base, making, for instance, salt and water. We don't have that here. In fact, we make an acid. Now, if we look at redox reactions, that would mean that both reduction and oxidation takes place. However, in this example, we can see that the oxidation numbers are unchanged, so it's not a redox reaction. Next up, let's think about combustion. So when something is combusted, it would be combusted in oxygen. That's an essential reactant. We don't have that here. So therefore, we can see that we don't have combustion taking place. So that leaves us with precipitation. That's our final answer. So that must be correct. But we also know that this is a precipitation reaction because we should know that lead sulfate is a solid. And that is the precipitate. So it is indeed a precipitation reaction. Here we're asked to identify the reason that hydrochloric acid is not used as the acid in potassium manganate 7 titrations. So this is a little fact that we should know, okay? They expect us to have this in our recall. We need to know that hydrochloric acid can be oxidized to chlorine by the manganate ions. So the answer to this question is C. It can oxidize to become chlorine. Now, if this was a fact you didn't know, then I would say turn this actual question and its answer into a flashcard and get memorising it. The mass spectrum of a metal has only the peaks shown in the diagram below. Here we're asked to identify the relative atomic mass of the metal. So to solve this, we need to know an equation for relative atomic mass. So we should know it's equal to the percentage times by the mass plus percentage times by the mass, and so on, and then divided by 100. So in this case, I can see that there's 4 different peaks. So I'm going to do 0.56 times by 84 for that first peak. Then I'm going to do 9.86 times 86 for the second peak. Then I'll do 87 times by 7.00 for the third peak. And finally, I'm going to do 82.58 times by 88 for that final peak. I'm going to add all of those together and then divide through by 100. So putting this into the calculator, I get 87.7, which I can see, looking at the options here, is equal to A. Now that was quite a lot of work, wasn't it? But I want to bring your attention to something here to show you a way that we could have got those marks without even doing any maths. So we're asked to find the relative atomic mass, which is the average, it's the mean weighted mass of those isotopes. If you look at the numbers that we have here, we've got masses ranging from 84 up to 88. Now, that's always going to average to somewhere between 84 and 88. If you look at A, B, C, and D, well, there's only one that could be, and that's A. So actually, we didn't actually need to do a single calculation to answer this. And so regardless, however we get our mark, the answer should be A, 87.7. do keep an eye out for little tricks like that that can save you so much work in these multiple choice questions. Here we're asked to select the correct answer with regards to the transition metal vanadium. So let's look through these one at a time. Here we've got the VO2 plus ion. Now we should recognise that that is not violet, it's actually yellow, so we can cross out A. Now if we look at B, we've got VO2 plus, which is blue. Great, so that's looking good. But let's check the oxidation state of the vanadium within that. We know that the oxygens within it are 2 minus. That means that the vanadium has to be 4 plus to make the overall charge of the VO2 plus ion 2 plus. So looking at B here, we can see it can't be that because that implies that the oxidation state should be 2 plus. So we've eliminated B now. So now let's have a look at C. Here we've got B3 plus, which is indeed green. And we can see the oxidation state here of C is 3 plus, and it's B3 plus, so that must be correct. So our answer to this question is C. Here we're asked to identify the type of bonding between the ligands and the metal ion in this complex ion. Now we should recognise that whenever we have these complex ions, we have the central metal ion coordinately bonded to the different ligands. So in this case, that cobalt is coordinately bonded to 6 of these water ligands. Now, a coordinate bond is otherwise known as a dative covalent bond. In this case, the water ligand has oxygens that have lone pairs that it's going to donate towards the cobalt to form those bonds. So the answer to this is B, dative covalent bond. And that will always be the case whenever we're talking about complex ions. Here we're asked to identify which atom is not an isotope of strontium. So to be able to answer this, let's look at the periodic table first and remind ourselves of what strontium's atomic number is and mass number. So the mass number is 87.6 and the atomic number or proton number is 38. Now that 38 tells us that every single isotope of strontium out there is going to have 38 protons. Because remember, that's what all isotopes have in common, the number of protons. However, the number of neutrons and therefore their mass number can change. So this is going to be the crux of this question. Here we're told the mass number. We know that mass number is equal to the sum of the number of protons plus the number of neutrons. So therefore, if we take this 38, this number of protons, and add it to all of these different neutrons, it should equal the respective mass number. So let's have a go at doing that for A first. So let's say we've got 38 protons plus 46 neutrons. That should give us a mass number equal to 84. And yes, it does. I can see that A has 46 neutrons and a mass number of 84. So that one is correct. That is an isotope of strontium. So for B, again, we're going to say we've got 38 protons plus 48 neutrons. And that adds up together to give us 86, which is the number in the table. So that must also be correct. So now for C, we've got 38 protons again. This time we've got 52 neutrons. Now 38 plus 52 gives us 90, which is not the value that's in the table. And therefore we know that C is not an isotope of strontium. Now we could leave it there and in the exam do, and just put that into your box. But let's check out D as well. 38 for the number of protons plus 50 for the neutrons does indeed give us 88. So C is definitely the correct answer. In the exam though, once you get to C, just put C down and then move on to the next question because time is of the essence with multiple choice questions. Here we're asked to calculate the amount of water produced by the complete combustion of 12 grams of methane. So the first thing we're going to need to do here is to write out the balanced equation for the complete combustion of methane. So methane has the formula CH4, and when it gets combusted, it reacts with O2, and because it's complete combustion, it makes CO2 and H2O. Now to balance this, I can see that the methane has 4 hydrogens, so that means I need 2 of the waters to get 4 hydrogens. By doing that and by doubling the waters, in total I now have 2 oxygens within those waters and 2 oxygens within the carbon dioxide as well. And therefore I'm going to need 2 oxygens as my reactants. So now I've got this balanced equation, I can calculate the amount of water that's needed. I know that we have a mass of 12 grams of methane. I can work out the MR of methane by doing 12 plus 4 times 1, which gives me 16. And now I can calculate the moles of methane by doing moles is equal to mass over molar mass. So in this case, that is 12 over 16, which gives us 0.75. So now we've got the moles of methane. We can now use molar ratios to find out how many moles we would have of water, which is what the question wants. I can see here I have a 1:2 ratio between the methane and the water. And so if I do 0.75 and I double it, I get that I have 1.5 moles of water. So I can also write down what the MR is of water. You're probably quite familiar with the fact that that is 18, but if you're not, then we're just doing it by doing 2 times 1 plus 16, which gives us 18. So now we've got all the information we need to get the mass. So mass is going to equal MR times by moles, and so that's going to be 18 times by 1.5, which gives us 27. So the mass of water produced by the complete combustion of 12 grams of methane is 27 grams D. An ion with a single positive charge and an atom have the same number of electrons. Here we're asked to identify which of the following statements is correct. Now this one's a little bit like a riddle. I think this is the sort of thing people might find conceptually quite confusing. So let's have a think about this. We've got an ion with a single positive charge, let's call it X plus, and an atom, let's call that Y. And we know they have the same number of electrons. Well, let's think this through. X plus is an ion. It's a positive ion, which means that it must have lost an electron to have become positively charged. So if it's lost an electron to become positively charged, let's think of what the atom X would have been like. The atom X must have had one more electron than Y, and therefore it must have had one more proton than Y as well. And this is using the fact that in an atom, the number of protons is equal to the number of electrons. So therefore we can make this conclusion then that X plus will also have one more proton than Y. And that's due to the fact that when we have an ion or an atom, the number of protons stays the same. It's only electrons that will change. So therefore we can cancel out the fact that the atom and the ion have the same atomic number, because they won't. X has one more proton than Y, so its atomic number will be bigger than Y. But point B here, the atomic number of the atom is one less than that of the ion. That is indeed correct. Let's return to our statement that X has one more proton than Y. So the atomic number of X is going to be one more than Y. And remember, X was our ion, so the ion has an atomic number one more than the atom. And if we just word that the other way around, then we can say that the atomic number of the atom is one less than that of the ion. So there we are. That is how we would explain this. And the answer is B. Here we're asked to identify which of the following molecules is or are planar. So let's have a look at these. Let's get started with the ethane molecule. What I would do is I would do a quick sketch of it if I wasn't sure, because I want to have a think about how many bonded and lone pairs are around each of those carbons. And I can see that there's 4 bonds around each of the carbons, and this means that we're going to have 4 bonded pairs around each carbon. We should be familiar with the fact that when we have 4 bonded pairs and no lone pairs, we have a tetrahedral shape. So we know that 1 is not an option, which immediately means we can eliminate the options of A and D. So now if we work out what 2 is, what shape 2 is, then that would be enough information now to work out if B or C is our answer. So this is HCN. So the H has a single bond to the carbon, and carbon has a triple bond to the nitrogen. Now around that carbon, we have 2 regions of bonding electrons. There are no regions of lone pairs. Now for that reason, we use the fact that when we have 2 regions of bonded electrons and no regions of lone pairs, then we have a planar arrangement. This is just going to be a linear shape, which means that it just lies in one plane. And therefore B is going to be correct because 2 is certainly going to be a planar molecule and 2 isn't an option in part C, so we can just eliminate that. And before we go any further, we just don't need to. We know that B must be the correct answer. Here we're asked to identify the number of straight chain structural isomers of C7H15Cl containing a chiral carbon atom. And the important thing for you to remember here is what a chiral carbon atom is. A chiral carbon atom is a carbon that has 4 different groups attached to it. They can't be the same. So what we're going to do here is be really methodical. I'm going to draw the different isomers of this molecule, and one by one I'm going to work out if they do contain a chiral carbon atom. So we know these need to be straight chain structural isomers. That already limits things quite a lot. So to start off with, I'm going to put the chlorine on the first carbon. So what I can see here, so if I have a look at this carbon on the end, I can see it has 2 hydrogens attached to it. Now that means that that carbon is not chiral because it doesn't fit the definition of having 4 different groups attached to it. Now, all of the other carbons here, I haven't filled in all of the bonds, but you should know that each of those carbons are going to have at least 2 hydrogens attached to them too, which again means that they're going to have the same group attached more than once, and they will not fulfill that definition of having 4 different groups attached to those carbons. So now let's have a go at redrawing this now. But this time let's have a go at putting that chlorine on the second carbon. Again, just being very methodical with this. So if we look at the carbon attached to that chlorine, I can see that it does actually have 4 different groups attached. It's got this pentyl group to the left, it's got a methyl group to the right, it's got a hydrogen above it and a chlorine below it. So that is one structural isomer that has a chiral carbon atom. So let's draw out another one. I've got a chain of 7 carbons again, and let's put the chlorine on the third carbon this time. Looking at this again, I can see it's got 4 different groups. It's got a butyl group over to the left, ethyl to the right, above it has a hydrogen, and below it has a chlorine. Those are 4 different groups, and so that is a second isomer. So let's have a look at this now. Let's put it on the 4th carbon. Now when I do this, I notice that to the left and the right, they have 3 carbon chains. Now they're just the same, so straight away we know that this is not an option. If we move the chlorine onto the 5th and the 6th and the 7th carbon, we don't actually get any different isomers. We get the same as when it was attached to the 3rd, the 2nd and the 1st carbon. So for that reason, we've come to an end. That's all of the straight chain structural isomers, and we've checked them all for chiral carbon atoms. We've only found 2 options there, so the answer is C, 2. Here we need to identify the bond with the greatest polarity. So there's a fact that we need to know here to answer this. So if you don't know this fact, make sure you make a note of it. We need to know that the species with the biggest electronegativity in the periodic table is fluorine. And so as a result, because all of these are paired with hydrogen, the fact that fluorine is the most electronegative of all of these means that that bond, the H to F bond, is going to be the one with the greatest polarity. So the answer to this is A, HF. In an experiment, magnesium metal was made to react with excess nitrogen gas, and the product obtained was reacted with H2O. The volume of the gas evolved at standard temperature and pressure was 672 centimetres cubed. Here we need to calculate the mass of Mg used in the experiment. Okay, so the first thing we need to do here is, of course, write down our balanced equations. So we should know that if magnesium reacts with nitrogen, we will make magnesium nitride. And because magnesium is a 2+ ion and nitrogen is a 3-, the formula of that will be Mg3n2, which of course means that we have 3 magnesiums in our balancing. So now that magnesium nitride is going to react with water and it is going to make MgO and NH3. So balancing this equation, we need 3 MgOs and we need 2 ammonias. And now we also need 3 H2Os. Now everything there should be balanced, and now we should be able to do our calculations. So in this question, we're told that the volume of gas evolved was 672 centimetres cubed. Now this gas is the ammonia. That's the only gas present that we make. So that volume corresponds to the volume of ammonia. We can use this fact to work out the number of moles of ammonia that we have. We are told in this question that 22.4 decimeters cubed is the volume occupied by 1 mole of gas. Now, because the volume of ammonia gas is given in centimeters cubed, we can convert 22.4 decimeter cubed to centimeter cubed simply by multiplying through by 1000. So here we know that 1 mole of gas is equal to 22,400 centimetres cubed of gas. Now, if we take that 672 and divide it by 22,400, we can calculate the moles of ammonia. And when I do that, I get 0.03. So now I'm going to have a look at my balanced equation. And I can see here that I have 0.03 moles of that gas, ammonia. And here, I need to eventually work out about magnesium. So what I'm going to do is use those moles of ammonia to work out the moles of magnesium nitride, which I can then take into the first equation and relate to the magnesium. Okay? So I can see clearly here that there is a 2-to-1 ratio between the ammonia and the magnesium nitride. That means that I need to take the moles of ammonia and divide it by 2. And that's what gives us 0.015 moles. Now that is the moles of magnesium nitride made in that previous equation. So I can take that into the previous equation. Now again here I can see I have a 3-to-1 ratio between the magnesium and the magnesium nitride. So if I take 0.015 and multiply it up by 3, then I get the number of moles of magnesium that I have. So I'm nearly there now, just by using these molar ratios. So I know that the moles of magnesium is 0.045 moles. I'm also told in this question to use the MR for magnesium as 24. So I know that mass equals Mr. moles. So in this case, the mass will be 24 times by 0.045. Now when I put this into the calculator, I end up getting 1.08 grams. And looking at the options here, I can see that that is option D. So the answer to this question is D, 1.08 grams. A small amount of potassium bromide was added to a beaker of water. The temperature of the water decreased from 25 degrees C to 18.1 degrees C. Identify which of the following combinations indicates the correct type of reaction and the reason. So what we need to observe here is that the temperature has decreased. We should understand that when the temperature of the water decreases, this means that we have an endothermic reaction. And the reason for this temperature decrease is because heat gets absorbed from the water into this reaction system. So the answer to this question is D. We have an endothermic reaction, which means that the heat gets absorbed. Here we need to identify which compounds are positional isomers of C4H8O2. Now, we would expect positional isomers to have the same functional groups, however, the position of those functional groups would have changed. So to answer this, let's have a go at drawing out these different structures and observing, well, what functional groups do they have, and have they changed position? And using that, we should be able to determine which compounds are positional isomers of C4H8O2. So let's get started here with compound I. I can see here that this has an ester linkage within it. So I'm going to write that on here. Got my ester linkage, great. Now, if I look at structure 2 now and I have a go at drawing this, I will be able to see which functional group it has. So let's get started with 2 now. So I've got CH3, CH2, CH2, and then COOH. Now I know that COOH is a carboxylic acid. So straight away, actually, I know that this is not a positional isomer of I. However, to answer this question, we need to have a look at the third option as well, because we're not sure yet. Could part 3 be a positional isomer of 2 or of 1? We need to have a go to work out. So here I can see I've got that COOC again, and that means we have an ester again. And in theory, we didn't need to draw these out. We could have just looked at the formulas and we could have deduced what functional groups they had as well. But see here, we can clearly see that they've got the same functional groups, but the position of that functional group has changed. So here I can see that our first and our third compounds are positional isomers of each other. So for that reason, I can see that the answer to this question is going to be C. Here we're asked to identify which of the following statements is correct regarding the nitration of benzoic acid. So let's look at point A. So the major organic product of this reaction is 4-nitrobenzoic acid. So of course we're starting here with benzoic acid, which is a benzene with a COOH attached to it. Now, what we need to recognise here to answer this is that the carboxylic acid group is an electron withdrawing group. Now, what that means is it is going to direct the electrophiles to attack the carbon at position 3. So that means it's not going to be 4-nitrobenzoic acid that we would make, it would be 3-nitrobenzoic acid. So that means that we can now just eliminate A. So now let's have a look at B. So benzoic acid is more easily nitrated than phenol, and let's have a think about this. Well, to answer this question, we're going to use the same fact that we did in A. So we should know that the carboxylic acid is that electron withdrawing group when attached to the benzene. And this actually makes it less reactive. So as a result, it's not going to be more easily nitrated than phenol. So we can eliminate B. So now C. This reaction is electrophilic addition. Well, it's not. Electrophilic addition is what we find with alkenes reacting with things like halogens and hydrogen. What we have here is electrophilic substitution. And so we can eliminate C straight away because we should be familiar with the fact that nitration of benzene of any form is electrophilic substitution. And so D must be correct. However, we should be familiar with the fact that sulfuric acid is a catalyst in the nitration of any of the benzenes. We should know that instinctively. So if we did just see this and recognise that before eliminating the rest, we could have just marched forward with D. However, that is the explanation for the other points as well. 2 experiments were carried out to find the rate of the following reaction. X plus Y makes Z. We're told that the rate equation for this reaction is rate equals K times by concentration of X times by concentration of Y squared. And we're asked to identify the initial rate of reaction in experiment 2. So what we want to do here is start off with the data in experiment 1 and substitute it in. So let's first just write down what we know. We know that rate equals K times by concentration of X times by the concentration of Y squared. So if we now substitute in what we're told in experiment 1, so of course we're told that the rate is just R, so we're just going to use that. It's just algebra, it's fine. So we've got R equals K times by 0.40 for X times by 0.10 squared for Y squared. Now when we have that 1 over 0.004, we actually get 250. So we can say that K equals 250 R. So now if we repeat the same thing now for experiment 2, but in place of K we put 250 R, then we will find what that initial rate is. So here we're going to get that the rate equals K, which we've just said is 250 R. And then we're going to times that by the concentration of X, which is 0.20. And then we'll times that by the concentration of Y squared, which is 0.20 squared. So now we'll sort of pause the R, but we'll put 250 times by 0.2 times by 0.2 squared into the calculator. I get 2, so we have 2R. So the answer to this is A, 2R. The compound below is analysed by proton NMR spectroscopy. Here we're asked to calculate how many peaks are observed in the proton NMR spectrum for this compound. So what this means, the number of peaks, is how many proton or hydrogen environments there are. So what I'm going to do here is I'm going to draw this compound a bit bigger and we're going to draw all over it and sum up where it has different proton environments. So here we are. So make sure that you have a good diagram when you're doing this. Either draw it out yourself or use the diagram in whatever question you have. So this is skeletal formula again, so we do need to be careful because we can't see all the hydrogens. Well, this pink region here, those hydrogens are all in the same environment. So that's one peak. These two hydrogens here are also in the same environment. So that's a second peak. Now we get to the benzene ring, okay? And we've got two different hydrogen environments in here, okay? So we've got these two hydrogens. Now, the reason why they're in a different environment to these two is because the blue ones are closer to the CH3 and further to that double bond O, and the purple ones are the other way around. Remember, it's that whole perspective. It's not just, oh, they're in a benzene ring, okay? It's the whole point of view. And finally, we've got these two H's which are attached to this carbon here. So counting those up, I can see I have 1, 2, 3, 4, 5 different proton environments. The main things to stress here are when you have your benzene, check out the symmetry, because different protons can still have either the same or different environments within that benzene. It all depends on the symmetry of the molecule. Make sure that you're thinking, what is it next to? And what's that next to? You know, it's the whole point of view, the whole way to the left and the whole way to the right. How does that differ? Another thing to stress is when it's a skeletal formula, don't forget that there are hydrogens there as well. By missing those out because you can't see them, that would be a very easy place to make a mistake and to lose your marks. So by all means, draw them out so that you can visually see them in the exam. A graph of ln K against 1 over T for a reaction has a gradient with a numerical value of minus 2,150. Calculate the activation energy in kilojoules per mole for this reaction. The ideal gas constant R is 8.31 joules per Kelvin per mole. So we should be familiar with this equation, ln K equals ln A minus EA over RT. Now, if we compare this to y equals mx over c, what we know on the y-axis is ln K, and we know on the x-axis is 1 over t. So by comparing these then, we can say that the gradient is going to equal minus EA over R, because that's what m is, the gradient. So we can use this little equality to solve for the activation energy. So let's make a note of that then. Gradient equals minus EA over R. And of course, we've been given the numerical value of the gradient to be minus 2150. So if we now try and rearrange this, we know that R equals 8.31. So activation energy is going to equal 2150. So as you can see here, that gives me an activation energy equal to 17,866.5 joules per mole. However, notice that they want it in kilojoules per mole. So we need to convert this from joules per mole to kilojoules per mole. And we do that by dividing through by 1000. So that gives us 17.8665 kilojoules per mole, which if we have a look at our answers, we can see that it is indeed A. Now a little tip here, activation energy can never be negative. It's not a change in energy like enthalpy change, which could have like a positive or a negative direction. It's just an energy. That's not a vector. It is just a scalar. It is a magnitude, the size of that energy. And therefore we could have immediately discounted B and C anyway. Okay, so there we go. The answer to this one is A. So here we need to identify the best representation for the following titration curve. Now here I can see that I have two vertical regions. I have two equivalence points. Now looking at all of the options here, this to me suggests that I have a diprotic acid. And so looking at all these options, that must mean that our answer to this one is A. So we must have a weak diprotic acid with a strong base, because by being diprotic, those two hydrogen ions, we get these two equivalence points. So the answer is A. So here we're asked to identify which compound is used as a standard for NMR chemical shift measurement. And this is purely a recall question, we just need to know this off by heart, and the answer is D. So the name of this is tetramethylsilane. We need to know its formula, and we also need to know its name, and we also need to know its structure. So it is a silicon atom in the middle with 4 methyl groups, which is why it's called tetramethylsilane. And so make sure that you're fully aware that this is what the standard is. It provides one small peak far to the right of the other peaks, and so all of the chemical shift values are measured relative to this. Now, all of these different options here in A, B and C, they are all possible solvents that might be used in an NMR. So there we have it. If you didn't know this, get learning it now. Here we're asked to identify which statement about the reaction of halogens with halide ions is incorrect. So we're looking for the wrong statement here. Now, first things first, these are all about reactivities really. So let's have a think about what the most reactive of the halogens is. So we should remember that as we move up the group, the reactivity increases. Now, using that fact, we can sort of run through each of these options and see if it is actually an option that would work. Okay, so here we've got F2 can oxidize bromide ions. So let's start by just writing down that reaction and seeing if it's possible. So F2 plus Br minus, we know that fluorine is more reactive than bromine. So what's going to happen is we're going to get F minus plus Br2. And we're going to balance that, and that's going to be F2 plus 2Br minus goes to 2F minus plus Br2. Okay, so we've got that reaction there. Now here we can see that the oxidation state of the bromine has gone from -1 up to 0. So yes, it has oxidized the bromide ions. So now we're going to have a very, very similar reaction with chlorine, because again, chlorine is higher in the reactivity series than bromine. So we could probably deduce there that this is another correct statement, but here's the reaction here. And again, it's because chlorine is more reactive than bromine that this reaction takes place. Now for the third option, we've got iodine reacting with bromide ions. And well, if we remember the reactivity, iodine is less reactive than bromine, and therefore actually no reaction takes place here. So that is our incorrect statement. Iodine cannot oxidize bromide ions. Here we're asked to identify which of the following gives 3-bromo-3-methylhexane as the major product when reacted with HBr. So first things first, let's just go through these methodically. So I'm going to draw out A now, just a bit clearer so it's easy to have a look at. And I need to imagine what will be the major product when it reacts with HBr. So of course, we're going to have electrophilic addition take place. We're going to break open that double bond, and the bromine is going to attach to the most stable carbocation. And in this particular question, we do actually have a tertiary carbocation. And so that is going to be where that bromine will bond. So if we have a look at what this ends up being then, and name it, and see how does it compare to 3-bromo-3-methylhexane, I can see when I start numbering this that I do indeed have 3-bromo-3-methylhexane. And so I know then that A is correct. So if I look through the options here, I can see that I can eliminate C and D because that doesn't include A. And that narrows us down now, because it's either going to be A and D only or A and C only. So I have no need to look at the option B here. I'm going to move straight on to C just methodically, and I'm going to start by drawing that out too. Now again, I know that I'm reacting this with HBr. So I know that the hydrogen will attach to one of the carbons of the CC double bond, and the bromine will attach to the other. So let's put this into practice then. Let's delete that double bond, and I'm going to bond to that our hydrogen and our bromine. Now here I can see then, if I number this, I end up making 3-bromo-4-methylhexane. And that is not 3-bromo-3-methylhexane, so we don't even need to go any further. We don't really need to go through the same process for D, because we've now eliminated B as an option, and so A is the only option left, so we can just write that down. And that's a really common way that we can work through these multiple choice questions. We don't really need to do the working for anything. We can use the process of elimination to get our answer. The reaction of the hydrocarbon myrcene with hydrogen gas produces a saturated alkane. Here we're asked to calculate the volume of hydrogen gas used when 340 milligrams of myrcene reacts with hydrogen in centimetres cubed. And we're told to assume that 1 mole of gas occupies a volume of 22.4 decimeters cubed at 273 Kelvin and 1 atmosphere pressure. So in order to do this, let's have a think about how many addition reactions there will be with the hydrogen and this myrcene molecule. I can see 3 CC double bonds, and each of those double bonds is going to bind to a hydrogen. They're going to react with a hydrogen. So due to that, we could essentially balance the equation by saying that myrcene plus 3 H2s makes this alkane. So we know the mass of myrcene, and we can use the MR to work out the number of moles. So first things first, let's get the MR of myrcene here. I can count up here that I have 10 carbons, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens there. So that is our molecular formula, which we can use to find the MR of myrcene. The MR will just be 10 times by 12 for the carbon, plus 16 times by 1 for the hydrogen. That leaves me there with an MR of 136. So using that, and the fact that we have 340 milligrams of myrcene, we can work out the number of moles that we have. So mass over MR, that's going to be 0.340, because we convert the milligrams to grams by dividing by 1,000, and then we divide it by the MR of 136. Now that leaves us with 2.5 times 10 to the minus 3 moles of myrcene. So we said that because there's 3 of these double bonds, it's going to react with 3 hydrogens. So we have a 1 to 3 relationship between the myrcene and the hydrogen. Therefore, we can get that the moles of hydrogen is 3 times 2.5 times 10 to the minus 3, and it is 7.5 times 10 to the minus 3. So next up, we were told that 1 mole of gas occupies 22.4 decimetre cubed, which, if we put it in centimetres cubed by timesing by 1000, we get that 1 mole of gas occupies 22,400 centimetres cubed. So we don't have 1 mole though, we've got 7.5 times 10 to the minus 3 moles of hydrogen. So if we times that by 22,400, I get 168 centimetres cubed, which I can see here is option C. So there we have it then. Our answer to this is going to be option C, and that is our answer. So in this particular question, I would say some of the main things that we needed to know is that every double bond is going to react with 1 hydrogen molecule. So in this case we had 3, so we needed 3 hydrogen molecules. We also needed to be able to deduce the MR from the skeletal formula. So that meant we needed to find the molecular formula using the skeletal formula. Now I always think this is a little bit tricky, particularly for finding the hydrogens. Remember that each carbon atom in this skeletal formula needs to bond to 4 different things. So a double bond counts as 2, but just go through it all and make sure that there are 4 bonds attached to each carbon. And if you can't find out what that bond is to, it's going to be a hydrogen, because we just don't write down the hydrogens in the skeletal formula. So there we have it. That is this question here. It's quite a tricky one, quite a lot to it, but we're always going to get that with multiple choices. Some will be longer than others. Identify which of the following statements is correct about the following compounds A and compound B. So looking at these, a lot of them talk about isomerism. So let's first start work out if they are even isomers, and we'll do that by working out their molecular formula. So I can see that compound A has 5 carbons, and I can see it's got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So its molecular formula is C5H8. Now let's do the same for B. So I can see that it has 1, 2, 3, 4, 5 carbons again. And counting up the hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8. So we also have 8 hydrogens. So here we can see that option A is actually correct. So that is our answer. We don't actually need to go any further. What we need to recognise here is that an isomer are 2 substances that have the same molecular formula but are different in some other way. So that could be that their structure is different, their arrangement in space is different. Here I can clearly see that their structure is different. One of these is branched and the other one isn't. So because they have that same molecular formula though, we can say that they are isomers. Now if we quickly run through why the others are incorrect. Part B says that compound B has a lower boiling point than compound A. Well, that's incorrect because the straight chain isomers will always have a higher boiling point. This is because there's more points of contact and therefore we're going to have more intermolecular forces and therefore a higher boiling point. For C, we're told that the IUPAC name of compound B is Z13-pentadiene. Now in this case, the part of that that's incorrect is the Z part. And that's because in this case, we can see, and I'll try and label this here for you, we can see that the highest priority groups around that CC double bond are on opposite sides. So that would actually be the E isomer that we have here. Finally, compound A has optical isomerism. Well, for optical isomerism to be present in an organic compound like this, we need to have a chiral carbon. Now that is going to be a carbon that has 4 different groups attached. And looking at the structure of A, I can see that none of those carbons have 4 different groups attached to them, and therefore it doesn't display optical isomerism. Identify which of the following statements is false regarding the colours of complexes formed by metal ions. Okay, so in part A, yes, this is correct. This complex ion is blue in colour. B is also correct. C is also correct. However, FeH2O6 3+ is not green in colour. We should know that this is purple in colour. It forms a purple solution. What they're trying to make us get confused with here is if it said FeH2O6 2+, then yes, that one would be green in colour. So just be really careful of the oxidation states because they will often have these different colour solutions. Here we're asked to calculate the enthalpy change of the following reaction. So here we can see we've got the hydrated copper sulfate salt, which is solid, goes to copper sulfate solid plus 5 H2Os. And we need the enthalpy change of that specific reaction. And we're told a couple of other enthalpy changes which are going to help us here. Here I'm going to write the reaction that they've given us, and I'm going to knock up a bit of a Hess cycle. Not one of the standard formation or combustion ones, but I'm going to use what they've given us here to construct it. I can see here they've got that the hydrated salt plus AQ goes to aqueous copper sulfate. So if I put aqueous copper sulfate on the bottom of this Hess cycle here, I can do an arrow going down from the solid hydrated salt to that aqueous copper sulfate, adding some aqueous along the arrow, and I know that that enthalpy change for that arrow is 11.5. If I look at the other little reaction that they have here, copper sulfate solid plus AQ goes to copper sulfate aqueous, I can do another arrow here going down, and I can label that as minus 66.1 because that is what that arrow represents. Now the water, we're not going to make it aqueous, it's just water, so that doesn't need its own arrow. So using Hess cycle, remember, you're going to go from the start to the end, and the enthalpy change will be the same regardless of the route that you take. So if I go down and then up and work out the enthalpy change of that pathway, then I will have the enthalpy change of this reaction. So as I go down, I can see I'm going in the same direction as that enthalpy change. So I've got 11.5. However, when I go up, I'm going in the opposite direction to the enthalpy change. So I'm going to reverse the sign of that enthalpy change. Instead of negative, I'm going to plus 66.1. And that gives us 77.6, which is A, which is our answer. Identify the statement that is not true about the bonding in sulfur dioxide molecules. So in order to do this, I'm going to knock up a quick dot and cross diagram of sulfur dioxide. So I know that sulfur and oxygen are all in group 6, and therefore they all have 6 electrons in their outer shell. Because there's double bonds here, I know that there's 2 shared pairs of electrons between sulfur and each oxygen atom. So here we have it. This is what the dot and cross diagram looks like. Here I can see that I have 2 regions of bonded pairs of electrons between the sulfurs and the oxygens. However, I also have 1 lone pair. And we know that lone pairs repel more than bonded pairs. And if it was just these bonded pairs, 2 sets of bonded pairs, then it would be linear. It would be 180. But the presence of that lone pair means that it's going to repel them away from each other, and we're going to have a non-linear or a bent shape. And so as you can see, looking through all these options, the bond angle is not 180 because it's not linear. There is clearly 1 lone pair on the sulfur. The molecule is indeed bent because of that lone pair, and there are definitely 2 lone pairs on each oxygen. So the answer to this one is A. Calcium hydroxide reacts with ammonium chloride as shown in the equation below. Here we're asked to identify the standard entropy change, delta S, for this reaction. And interestingly here, there's numbers, but they haven't given us any numbers to work it out with. And that could throw a lot of students and make them think, well, this is impossible, and just move on to the next one. This is wrong, and move on to the next one. However, let's write out this equation a bit bigger so that we can have a look. The thing we want to keep an eye out for here first is the state symbols. We can see that looking at the reactants here, all of the state symbols are solid. However, when we have a look onto the next side of this reaction, we have a solid, we have a gas, and we also have a liquid. And we should know that the entropy of a solid is less than the entropy of a liquid, and the entropy of a liquid is less than the entropy of a gas. Because of course entropy is a measure of disorder, and so gases are more disordered than liquids and solids, and liquids are more disordered than solids. So using that fact, we can see that the products have more entropy. And therefore, when we move from the reactants to the products, we can see that the entropy has increased. Now this means that the entropy change is going to be positive. And if we look at the options here, you can see that there's only one option that is positive. And that is how we work this out. And this is how multiple choice questions can be quite clever, really, because they can mislead you and they can make you feel that there's something wrong with a question or that you just clearly had no idea. Whereas really, we can just deduce it from the information given. We don't need to actually calculate in this case. The pH value of a solution which contains a weak acid HA and its sodium salt is alpha. The ratio of the concentration of HA to NaA is increased by 10 times. Here we're asked to identify the new pH value of the solution. So here let's start by reminding ourselves that that initial pH value was equal to alpha. So here we're told that the ratio of the concentration of HA to NaA is increased 10 times. Let's remind ourselves of what that actually means by reminding ourselves of the Ka equation. So we should know that when we have a weak acid, Ka equals the concentration of H plus multiplied by the concentration of A minus divided by the concentration of HA. And if we rearrange this to get that ratio of HA to A minus, which is where the NaA is coming into this, we can see that we get HA over A minus is equal to H plus over Ka. Now, obviously I'm being very thorough here, but it never hurts to be thorough when trying to understand something. So I've got this ratio of HA to A minus, which just means that they're divided by each other. And we know that ratio is 10 times bigger. Well, because Ka is a constant, that means the H plus concentration must have got 10 times bigger. So we should be familiar with this little fact. We should be familiar with the fact that if the concentration of H plus gets 10 times bigger, the pH of the solution will decrease by 1. And so in this case here, we know that it was originally alpha, and so if it's decreased by 1, then the answer will be A, alpha minus 1. And so that's our answer to this one. The first 5 ionization energies of an element are given below. Here we need to identify which group of the periodic table A can be found. Okay, so this is all about looking for where the big jump is. And I can see that the big jump occurs between removing electron number 3 and removing electron number 4. Now this is really, really important because let's have a think about what this means. It means that when we remove the first, the second and the third electron, it only required a little bit of extra energy. But for so much more energy to be required to remove that fourth electron must mean something big has happened. It must mean that we're removing that fourth electron from a shell which is much closer to the nucleus. So this is where we've broken into that new shell. And from this we can deduce these first 3 are being removed from one shell and the rest are being removed from a shell closer to the nucleus. Now this means that we have 3 electrons in our outermost shell, which must mean that we're coming from group 3. And so the answer here is C.
Ouch! This is why in some videos I'll explain scratches.